Hi, I'm Partha Banerjee from Electro-Optics and Electrical and Computer Engineering. This is my lab. I call it sometimes by different names. The current short form for it is, I think, HAM, standing for Holography and Metamaterials. And what we do in the lab are experiments on optics. These are optical tables where we mainly do work on holography and characterization of optical materials, particularly optical metamaterials, of which you might hear a little bit more later on. Way out here in the back are, as you can see, a clean bench where we essentially make some of our materials. We used to do chemical deposition of nanoparticles, and characterization of the nanoparticles is done partly here and partly in the optical benches on the other side of the room. Well, I've been involved with a lot of different things over the years, and my background really has been an electrical engineer, but then in my PhD and later on have worked a lot with waves, essentially. And I started out in my PhD working on water waves. Although I was an electrical engineer, that was my dissertation. And then later on in life, I started to work with optical waves, and more particularly nonlinear optical waves. And then I digressed to other areas in optics. One of them was holography. That's one of the things I'm working on now. Holography has been around for a long time, since the invention of the laser, and that was way out in the 60s. But now, over the last, I would say, probably 10, 15 years, a lot of people have been working on digital holography, which means you generate the hologram, essentially record it on a digital camera, and then you reconstruct the image, which is the three-dimensional image, numerically by doing computations from all the data you have gathered on the computer. And some of the pictures that you saw right there were pictures of digital holograms, really. And they would be numerically reconstructed in order to generate the three-dimensional object. The other thing that I've been also working on in the lab, and that's something I also have on the cover page of the book, is metamaterials. And metamaterials have been in prominence over the last, I would say, 10 years or so, because of their very strange properties. So I grew up in Calcutta, India, and I was there from when I was born in '57 till 1974, when I went off to undergraduate school in a city close to Calcutta. And after I graduated from there, I came to the US, to the University of Iowa. My first job after I graduated was in a very snowy place, Syracuse University. And I think one fine morning in February, when it was snowing hard, the chair, Dr. Balbanian, came into my office and said that I won the National Science Foundation's Presidential Investigator Award. I was certainly very pleased to hear that, because it's certainly given to a very select group of young researchers. These days, the PYI award is now called the Career Award, and a lot of faculty, young faculty especially, should be encouraged to apply for it. Because for one thing, what it does is it gives you a fixed amount of money to do research, and you can expand on that money by getting, for instance, extra grants from industry. It did help me quite a lot. When I was at Syracuse, I got my 5 years worth of money from the NSF to do work in the area of my expertise, and I was able to interest GE, which was a big presence at Syracuse at that time, to cost share my work. So I did benefit quite a bit. I would certainly encourage all young faculty to apply for that award. It's a very prestigious award, but at the same time gives you a lot of liberty to work on what you want. My interest in science really has come from the fact that, you know, I think when I was a young guy, my dad certainly prodded me on to science. And in fact, when I was 6 years old, he asked me a question. He pointed to me the sky, and he showed me the contrails of an aircraft. And sure enough, of course, he was an aircraft engineer, but he asked me where they came from, and after scratching my head, I didn't know too much. I blurted out that, well, those are condensation of water droplets. You know, much later on, the work we are doing currently has to do with how light disperses from water droplets. It's a process called me resonance. And so in this experiment, what's being done is holograms are being generated for water droplets. And the water droplets really, in this case, are air bubbles that are being blown into the water tank. And what you would see on this computer screen are what are called inline holograms of those air bubbles. For instance, as you see, these places over here where you see these circles, these are the locations of the air bubbles.
We try to do holograms of all sorts of things. So this is just a dime, right? And try to make these reflective holograms of a dime, so we illuminate it like that.
One of the work that we do in the area of digital holography, as you know, it has a lot of applications in 3D imaging, how to generate 3D images very efficiently. And as you know, you can buy 3D TVs these days. This might be an alternate way of generating 3D images. That's the reason we are working on digital holography. Besides, holography has been around for a long time, since the invention of the laser, and that was way out in the 60s. But now, over the last, I would say, probably 10, 15 years, a lot of people have been working on digital holography, which means you generate the hologram, essentially record it on a digital camera, and then you reconstruct the image, which is the three-dimensional image, numerically by doing computations from all the data you have gathered on the computer. We have been involved with Army projects where we've used digital holography to, for instance, measure the attitude of airplanes testing in a wind tunnel. And by attitude, I mean pitch, yaw, and roll. They don't have any personal attitudes. We have also used it to do holograms of little water droplets that may impact a high velocity radome, for instance. And currently in the lab, work is going on detecting very small cracks that might develop or deformations that might develop when these water particles would hit a radome. The work on metamaterials has its applications in developing, for instance, efficient coatings on, say, photovoltaic devices that can allow more light to be absorbed and thereby increase the efficiency of those devices.
There's always speckle. The speckle is actually a phenomena that's not on the paper. It's in your eye. So you're seeing a different speckle pattern than I am, and you're seeing a different one. And the camera will actually capture a different one because of the iris of the camera. It's actually determined by the iris.
Can you do that one more time for me? Thanks.
Yeah, as a matter of fact, I'm going to do some other cool stuff here. I'm going to try to show you some diffraction rings here. So this is just kind of a procedure we'll do to a line. So now,
that's actually
yeah,
That's nice.
so it's nice and uniform, but I have all those diffraction rings. So what I try to do when I'm aligning the beams, I try to get rid of those diffraction rings. So I slowly move this, and then I move this a little bit. I move this just a little bit. I'll move this a little more. And I'll adjust. And it's kind of a tedious process.
So you only
But
want
notice how I'm getting rid of those rings now, right? Yeah, I want that central peak to be as large as possible, as large and as uniform as possible. So I'm trying to get all the power into the central peak here.
So I have developed a lot of new courses over my years of academia, and certainly stuff that I try to teach more so at the graduate level are very often derived from our research. The other thing that I've been also working on in the lab, and that's something I also have on the cover page of the book, is metamaterials. And metamaterials have been in prominence over the last, I would say, 10 years or so because of their very strange properties. One of the commonly known properties known to the public is cloaking. How you would take a metamaterials, say, gown, and then make yourself invisible.
What is it? Some kind of cloak.
Well, let's see then. Put it on.
Whoa!
My body's gone. I know what that is. That's an invisibility cloak. I'm invisible.
Well, we are not up to that point as yet, but one of the properties of metamaterials is that it has a negative refractive index. And we have been able to actually make a material that has a negative refractive index at visible wavelengths, namely with blue light. So the metamaterials we make in the lab are made of nanoparticles. In fact, they are made of a binary mixture of nanoparticles. Students form an integral part of research, and as a teacher, really our job should be to educate students. And those students who are interested in doing research should be educated on how to do research. New things are being developed all the time, and students should get to know about it. When I worked with GE, I was actually trying to help them with work on optical computing at that time and optical algorithms. And I'm very excited to see that there is a joint venture between GE and UD coming right here on campus. And I'm sure in this particular case, it'll open up a lot of collaborative research between our faculty and GE. Yes, I did come from India to study my graduate education in this country. I came in '79, and then I graduated with my PhD in '83. And certainly over the years, I have had plenty of younger folks join Syracuse, University of Alabama in Huntsville, and certainly here, who are from foreign lands. And I try to help them as faculty mentors whenever possible. Get them settled down, encourage them to continue doing research, and also, most importantly, I try to tell them how to interact with foreign students. As you know, in this university there's a lot of students from China, from India, certainly increasing number from the Middle East. We should actually pay attention to their needs and try to cater to their interests, try to help them out because they are in a foreign environment, and try to see that we can get the most out of them.